Earlier, I planned this lecture to be 3 small consecutive lectures and providing you with a number of exercises. But it seems that because I won't be there to the class, so it has to be incorporated together into one lecture. And this lecture will be about convolution and the LTI system properties. First, let us revisit the output of LTI system and the way that we can calculate the output last time. We can calculate the output of an LTI system using the convolution sum. That is, the output yn is the summation of the shifted version of impulse response multiplied by the value of input, and when you sum them together, which this is the output of the small version, the small impulses that is scaled by the input values. This operation is called convolution, and we will look at it in terms of an easier way in this lecture. The same equation, we can think of it in terms of geometric. That is, in terms of the time operation. That is, this is the output y at time n. K here is the running sum index from minus infinite to infinite. And this is the multiplication between the input and hn minus k, which is the reversed and shifted version of impulse response. So we can calculate the convolution process by doing the reverse operation and the shift operations, and then multiply it with input, and then calculate the summation of the multiplication. The first step to do convolution is to reverse. Let's look at this example. Suppose that the signal xn is minus delta n minus 1 plus delta n plus 2 delta n plus 1. So there are 3 stems, 3 bars, and hn equal delta n plus 1 plus delta n. So there are 2 bars at minus 1 and 0. And the idea is to find the convolution, which is summation of k equal minus infinite to infinite of sk hn minus k. So let's start by looking at the impulse response hn. Suppose if we look at h here alone, we would get hk looks like this. hk, you have the bar when k equals 0 and the bar when k equals minus 1. The flipped version of this hk is h minus k. The h minus k would be the flipped version of hk. That is, to have a bar at 0 and another bar at 1 instead of minus 1. Then shift this h minus k by each n. So if n equal minus 2, like this, then h minus k is shifted to the left by 2 units. So you have h minus 2 minus k like this. Why shifted to minus 2? Because when we look at the input, the values start from around minus 1 to 1. So let's shift it to the nearby values of the input, and we'll see if they are overlapped or not. So this is h minus 2 minus k. So this is the shifted version of the impulse response, h minus 2 minus k, and this is xk. When you multiply them together, you multiply them point by point. So multiply them sample wise. That means 0 here. That means at the minus 2 point, you got this 1 minus 0 equals 0. And at the minus 1 point, you got 1 minus something here equal this bar. So this is xk multiplied by h minus 2 minus k, because the remaining points here are 0. Then by summing them all, summing this multiplication, meaning that you calculate a scalar value of this multiplication, then you get the values equal to the height of this bar. Then we repeat this step again for each n. Now it should be -1, 0, and so on, 1 and 2. And at -1, let's repeat it again. At -1, at n equal -1, h minus k would be shifted to the left. Then multiply the shifted impulse, the reversed and shifted impulse with input. You have this equal to, at the -1 position, you get this bar multiplying by 1 equals this bar. And at 0, you get this bar equal 1 multiplied by this bar, so equal 1 here. And this is 0 multiplied by something like -1 here, so you get 0, and so on. This is the multiplication of xk with h -1 minus k, the shifted and reversed version of impulse. Then calculate the summation of this multiplication. Then you get this bar equal 2, this bar equal 1, then it equals 3. Meaning that the output at time, or if I go to the previous example, this is the output at n equals -2. The output at n equals -2 equals 2. And this is the output at n equals -1. There is a very nice Java applet created to explain this process. I will switch to that to show you how it works. The upper left panel here illustrates the input signals, and this upper right panel illustrates the impulse response. Suppose that input signal looks like this, 4 bars, and the output signal looks like this, also 4 bar. Then if I click it here, then I get this is n equal -16. This is the green bars here illustrate xn minus k, and this one illustrate hk. You can see that in this example, the creator reversed the notion. Instead of using hn minus k, he used xn minus k instead, but they are quite similar. So when you move it closer, when it overlaps, you can see that there is a value of multiplication when it overlaps, and there is a certain output there. When it overlaps, the values down here equal the summation of this multiplication, and you can see that the values will last until the two are not overlapped, and this is the output. So you can play with this further and practice in the class. What happens if the input is a CT signals? If the input is a CT signal, then it is not just point-by-point calculation, but we are talking about area under the curve here. So you can think, instead of thinking of the CT signals as a combination of unit impulse, you can think of a CT signals as a linear combination of a rectangular pulse. This is a rectangular pulse. So these signals consist of a combination of rectangular pulse. Then each rectangular pulse, when you decrease the amount of time, then you get impulse somehow. You can approximate the signal using rectangular function. When you multiply delta with signal, you get the samples of that signal. So if you multiply delta t with x, you get x0 out, which is the value of x at time 0. When you multiply this with delta, which you can think of the width, think of it as the width of the rectangular pulse, then you get the rectangular area of the rectangular pulse at time 0. Then if you shift it by delta, the capital delta here, then you get the rectangular pulse at time delta. If you shift it by minus delta, then you get the rectangular pulse at the time minus delta, and so on. Then you can write it as the original signal is the summation of the xk delta and delta t minus k delta, which is the and multiplied by delta here. This is, you can think of this term as rectangular pulse, and the signal xt can be approximated by the summation of this small rectangular pulse. And then when you take the limit to 0 of this equation, it will make this equation transform into the continuous time equation. That is xt equal the integrate of x tau. Tau is a dummy variable. Delta t minus tau d tau from minus infinite to infinite. This is actually just like in the discrete time version, because as you can see here, the input is described as the running integral of the value of the input multiplied by the impulse. So it's like you multiply the impulse with the signal xt. If you multiply it at time equals 0, you get x0 delta 0. It will translate or move this impulse from minus infinite to infinite. Then you get the actual signal. So for an LTI system, if you give a system with delta t, just like in the DT system, you get the output ht. So if you give the input with the integrate of from minus infinite to infinite of x tau delta t minus tau d tau, the output would be integrate of from minus infinite to infinite of x tau ht minus tau, which is the same equation as in the DT domain, the very similar equation, and we call this the convolution sum of CT LTI system. You can play with this demonstration online by yourself. It will illustrate the process of convolution in continuous time domain, which actually is quite similar to what we learned in discrete time domain. The summary of convolution integrals looks like this. That is, in the discrete time domain, you get the difference is only in terms of the summation. Here you have discrete summation. In the continuous time domain, you have integral, but the rest are the same, that you need to flip it, the signal, and then shift them. And instead of summing the bars, you need to integrate for the area under the curve for each interval. Now let's talk about the properties of LTI systems. The LTI system have properties just like linear algebra. That is, if you can calculate output yn from the output yn or yt from input x and the system h, then you can switch side. There is a commutative properties. There is a distributive property. That is, if you apply input x into two systems h1 and h2, then it equals to applying x to h1 and applying x to h2. So it's like applying x to a separate systems, then combine them later, would be equal to apply x to a combined systems to get the same output. This property is the distributive properties. LTI system has associative properties. That is, if you apply the input x into the convolution of two systems, the combination of two systems, h1 and h2. We use convolution because the system is in a cascade or a series configuration. In this slide, you can see that the systems, we use plus here because the system is in the parallel configuration. So in the series configuration, we use convolution because the output of one system form the input to another system. That means they are in convolution manner. So if we talk about something like the output of one system, this is the output of one system, and because it is an input of another system, it has to do the convolution with another system here. So if we have xt passing through h1 and h2 two systems to get y, then it equals to having xt and passing through an integrated system H1 H2 or an integrated system H2 H1. Now let's talk about a more familiar properties. The invertibility. Invertibility indicates that when you give the system with one input and get one type of output, if you fetch another system that is an inverse system of the old system with the output, you should expect to have input. So if the system is invertible, then it should have this H1T or H1N. That is when you convolute it with the impulse response, then you will get the delta N, the impulse. What does it mean by this? It means that if you give the input xt to the system ht and then you get yt, if you have an inverse system h1t, then you fetch this system with yt, you would get an output wt, which if h1 is an inverse of h, then wt would be xt. And the convolution of these two according to an earlier properties, that is you can convolute them together, would be an identity system delta t. And whatever convolute with delta would be the same old original signals. If the system is causal, then Hn impulse or Ht impulse response has to be equaling to 0 when the time index is less than 0. Imagine that what will happen if the values of the time index when n is less than 0 become more than 1. If you consider this, you will see the answer. Let's consider this non-causal system yn equal xn minus 1. If we substitute y with h, then here we have x as delta. So hn equal delta n plus 1. Delta n plus 1 has a value of 1 at time minus 1, time less than 0. So you can see that whenever the system relies on the future input, what you have is that the delta would be in the negative side of the impulse response. If the system is stable, then when you calculate the summation of absolute value of hk, you will get the value less than infinity. This is a very nice property of LTI system. That is, you can easily calculate whether the system is stable or not stable by just considering the impulse response. This is the end of the advanced video lecture. Since I won't be there to teach you personally in the class, so you have to rely a lot on yourself, and I hope that more or less this video could help you a little bit. Although I know that it's not like personal communications that we have in the classroom. So if you have any questions, please do not hesitate to contact me via emails or Facebook. I will respond as soon as I can, as I mention every time. And when I come back, feel free to drop by to talk about and to catching up on the topics that I left you to study by yourself here. See you when I'm back next month. Bye.